Okay, today we're going to go over 5.2, which is trisectors and triangles. Mainly, we're going to talk about perpendicular bisectors again and angle bisectors again. Two important vocabulary words we're going to need to learn today. One is concurrent, and the other is point of concurrency. Concurrent means when we have three different lines and they all intersect at the same spot. So if I have three lines here, and they're all going through, and they intersect at the same spot, we say that these three lines are concurrent. So concurrent is when we have three or more lines that intersect at the same location. We're only going to use three for our purposes, but you can have like 4 or 5 or even more. The point of concurrency is simply the point where they intersect. So the point of concurrency will be that point right there where they actually intersect. And we're going to discuss 4 different types of points of concurrency over the next couple of days in class, 2 of which we're going to discuss on this video today. All right, the first one we're going to work with is the perpendicular bisector. So, draw in your favorite triangle. Let's see, let's draw one here. Mine kind of looks almost like a right triangle. You can use whatever kind of triangle you like. It works for all of them. So what we're going to do is we're going to draw in perpendicular bisectors. Remember, perpendicular means the line has to be 90 degrees with another line. Bisectors means he needs to cut it perfectly in half. This is the bisecting mean. Remember, bi means 2. So we're going to pick this side. We're going to try to kind of eyeball it today. We're going to kind of eyeball it just for our notes. And we're going to roughly find the middle of that side. And I'm going to draw a line coming out from that side at a 90-degree angle. All right? So that's my perpendicular bisector. It's going to cut this side perfectly in half. All right, perpendicular bisector. Next, I am going to find the middle of another side. Like I said, we're just kind of eyeballing it up today, so we divide that perfectly in half. This is going to come down. That's going to be perpendicular. So we have 2 perpendicular bisectors so far. All right, next we're going to find the middle of the third side, almost up to the hypotenuse. But the way it's turning out, I don't think that angle is going to be 90 degrees. I think it's going to be acute. So we find the middle of this one right about here. And if we bisect it in half, that means these 2 sides are congruent to each other. We're going to draw a line 90 degrees up through there. So there I have 1, 2, 3 perpendicular bisectors. All right, if you notice, they all intersect at the same point. That's the point of concurrency for perpendicular bisectors. It happens to have a special name now. We call the point of concurrency the circumcenter. Now, it all depends on what kind of triangle you drew. This is more like an acute triangle where all the angles are less than 90 degrees. So my circumcenter was inside the triangle. If it was more of a 90 degree or right triangle, my circumcenter would have ended up on the hypotenuse. If it was an obtuse triangle, then my circumcenter would have ended up on the outside of my triangle. But here it's on the inside because I'm guessing that's probably less than 90 degrees. Now, what's so special about the circumcenter or the point of concurrency? Well, this point of concurrency now, it's equal distance to all 3 corners or angles of the triangle. We call them vertices. Vertices is just plural for vertex. So if I was to draw a dotted line in here, a dotted line in here, and a dotted line up here. Basically, I'm drawing little dotted lines on the point of concurrency out to my 3 corners. All of these distances would be congruent with each other. It's a lot of lines on there, I know. But all of them will be equal distance to each other. So whenever we have perpendicular bisectors, the circumcenter or the point of concurrency is equal distance to all the different vertices of the triangle. Now, what else can we do with this? Well, what we've actually created is we've created the center part of a circle. So we're going to draw a circle around the triangle. And we want the triangle to kind of touch all three vertices of this. This is the toughest part, drawing an accurate triangle. There we go. That's not too bad. I have done a little bit better in class from time to time. Takes a little bit of practice. All right, so what we have here, basically we've created this is the center of our circle. The circumcenter is actually the center of our circle. And now the red lines, since they go out to the edges or the corners, of the triangle, we've created the radius of the triangle. So we can use this in later math. Whenever we draw a circle around the triangle, we say it's circumscribed around the triangle. So this circle is circumscribed. All right, around the triangle. All right, so you won't see too many problems with the actual circle on there. That usually comes later on when we're dealing with circles and some higher levels of math. But it basically creates, we put it on here for right now in our notes because it creates the radius. All right, that's perpendicular bisectors. Let's go on to angle bisectors. We're going to do the same thing here. We're going to draw a triangle. And now instead of doing perpendicular bisectors by cutting a side in half, we're going to cut the angles in half. So to the best of your ability, draw in angle bisectors of all three angles. There's one, which makes these two angles congruent because it cuts the big angle in half. It makes both of those congruent. Kind of cut down through here. It makes these two angles congruent. Right? We've already found where that point of concurrency is going to be. And then through here, if we divide that in half, draw the third one in there. There we go. So now we have 1, 2, 3 angle bisectors. We have another point of concurrency. This one is called the incenter. Because guess what? Guess where it's located? That's right. It's located in the center of the triangle. So we can find the actual center of a triangle. Now, the last one was equal distance to all the vertices. But this one comes in from the vertices, so this one's going to be equal distance to all the sides. So if I was to draw a straight line down to that side at a 90-degree angle, because remember, we have to go straight to the side, and then straight over to this side at 90 degrees, and then straight over to this side at 90 degrees. All three of those would be the same length. It would be equidistant. And you're going to use a lot more when it comes to this stuff, these things being equal distance. All right? We can also draw another circle on here. This circle will be on the inside of the triangle where it reaches out and touches all the different sides. So once again, the incenter would be the center of that smaller circle. And we also have more radii as we've created this. All right, so that's the incenter. The incenter is the point of concurrency when we have angle bisectors. All right, let's do a couple of practice problems on today's class. All right, so we have here, it says if QP is 3 times x plus 1 and RP is equals 5x minus 3, what is the radius of the inscribed circle of JKL? Well, it doesn't have a circle on the inside, but we know since it's talking about inscribed circle, we know that we're dealing with angle bisectors here. So we know that QP and RP would be the same distance. So it would be the radii. So if they're the same distance, all we're going to do is set both of these terms equal to each other. All right, both of these algebraic expressions, equals 5x minus 3. Right, because QP and RP are the same distance. All right, so once again, if I work this out, I get 3x plus 3. As I distribute the 3 into my parentheses, equals 5x minus 3. Let's fix that. I move my x's over. So I get 3. If I subtract 3x from both sides, I get 2x minus 3. Now if I add 3x to both, if I add 3 to both sides, I get 6 equals 2x. Divide both sides by 2. X equals 3. All right? But it doesn't want x. It wants the distance or the radius. All right, well, I can use either expression because they're both the same distance. So let's use 5x minus 3, shall we? So if I had 5x minus 3, it'd be 5 times my value of x, which is 3, minus 3, which gives me 15, minus 3, which is 12. All right? There we go. That's our first example problem. All right, next problem. It's a double dipper. We're going to get two for the price of one. All right, so it says if the measure of BAF is 15 degrees and the measure of CBF is 52 degrees, what is the measure of ACF? Now, keep in mind, if you're watching the video, you can hit pause, try to solve this yourself, and then we can come back and get the answer. So you can hit pause right now. Hit pause. All right, welcome back. So if we're given information in a word problem, the best thing to do is to add it to our diagram. So we're going to make this 15 degrees. Because it says BAF is 15 degrees. CBF right here, this is 52 degrees. It wants to know the measure of ACF. It wants to know that angle right there. All right, it wants to know that angle right in the middle there. Not the whole angle, just half of it. Because remember, that's an angle bisector. All right, so we have an angle bisector. We know we have to solve for this angle down there. So that's 15 degrees. The best way to do this is what will be the total of that big angle? Well, 15 and 15 would mean that angle is 30 degrees. This angle down here, the larger angle, would be 104 degrees. Because 52 plus 52 is 104. Now, if we figure out the big angle over here and didn't take half of it, we can get our answer. And we know that all three angles, when added together, equal 180 degrees. So if I take 180 and I subtract 134, which I get from adding 104 and 130 together, I get 46. Divide that by 2 to evenly distribute it amongst the two different angles. 46 divided by 2 is 23 degrees. So we know it. My first question, my answer, the measure of ACF is 23 degrees. All right. Next problem. All right, it says EF is 3y minus 5, and DF is 2y plus 4. All right, so it's talking about this side, this segment right here, and this segment right here. Now remember, that's an incenter. So these two distances are equidistant, or they're congruent. So I can set both of these equal to each other. It says, what is the distance, though, from F out to AB? So let's know this distance right here. Well, all three are exactly the same. They're all the radius of a circle if we drew a circle and inscribed circle on the inside. So all we need to do is set 3y minus 5 equal to 2y plus 4. Excuse me. If I take away 2y from both sides, they give me y minus 5 equals 4. If I add 5 to both sides, I get y equals 9. And once again, all we need is a distance. We can use either expression. So I guess let's use 3y minus 5. I already know what y is. Y is 9. So 3 times 9 would be 27. Minus 5 is 22. So the distance there will be 22. You can even check your work by doing the other one. So 2 times 9 would be 18. Plus 4 is, once again, is 22. All right, so that is perpendicular bisectors and angle bisectors. If you have any questions, please ask me in class.